Let's go ahead and get started. I'm Dan Bicus at CIRA, and I'm pleased to introduce the Forecast Decision Training Division Go 16 Applications webinar for today, 12 July. And our presenter today is Dan Lindsay, who is with Noah Nesdis Center for Satellite Applications and Research here at CIRA in Fort Collins. Before we begin, we'll cover a few logistics. First of all these are recorded, and if you want to see the recording afterwards, you can go to the visit web pages, look for the satellite chat library, and you'll see the video recording of all past webinars. Also, we're looking for speakers. Let us know if you'd like to lead one of these, and you can feel free to contact either myself, Dan Bicus, or Scott Lindstrom if you'd like to lead one of these in the future. In terms of what we'll do for today, we'll give about 20 minutes for our speaker. You can send questions via the GoTo chat, or we'll also have a question and answer period via the phone right after Dan is done talking. We'll be done by 17:30, so we'll definitely finish before 30 minutes. Remember, do not press hold, and also mute your phone when you're not speaking. So with that, I'll turn it over to Dan.
All right, thanks, Dan. Can you pass me? Okay, there we go. All right, can you guys see the title screen there? And is the audio okay?
Yeah, I can hear you, Dan.
Okay, great. All right, well, thanks a lot, Dan. I appreciate the invitation to talk about the Go 16 Geocolor product. A little background. So you may have seen some of this particular product on social media, particularly from the NOAA satellites feed of Facebook and Twitter and other things. This was what we're looking at here is actually the first light image that was released by Nesdis back in the end of January at the first day of the AMS meeting in Seattle. This is work that I do in collaboration with a number of others, particularly Steve Miller and Curtis Seaman here at CIRA, as well as Deb Molinar, who's also a NOAA employee at CIRA, along with myself. So the goal here today is basically to introduce you to this product, explain briefly how it's created, and then talk about some applications specifically for smoke and dust identification. So first, I'm not going to go into the gory details of this busy chart, but if you look at the first column, this just shows the spectral bands that are aboard the GOES-R ABI. And on the left over here, you can see the central wavelengths. They're ordered from lowest to highest wavelength. And you'll notice that the blue band, or the colors here represent the spectral range of the particular colors within the visible spectrum. So 0.47 is blue, 0.51 is green, and 0.64 is red. Now, in order to make a true color image, you need a component of blue, green, and red. And that is what we've been doing with the Himawari, Advanced Himawari Imager, which is the second column here, for several years now. You may have seen some of that, including in a BAMS paper last fall. However, if you look at the GOES-R ABI, and as you probably know, there is no band around the green area of around 0.51. So the first challenge here is to figure out how to deal with that. How are we going to make true color imagery since we don't have a green component? So the first step before we simulate a green band is we do something called Rayleigh Corrections. So there's something called molecular scatter or Rayleigh scatter that occurs of the sunlight that's coming in by the gaseous atmosphere. And if you look at the screenshots at the bottom, this is actually from Himawari, which is a similar instrument, except the ABI doesn't have the green, as I said. But if you look at the contrast between the ground and the clouds, it actually gets quite a bit greater as you go to the longer wavelengths. In other words, blue is a lot more milky than the other wavelengths, and this is due to molecular scatter of blue, preferentially the wavelengths around 0.47 microns. And this is actually the reason the sky is blue. So the first thing that we do is we correct for this by basically understanding the physics of what's going on as a function of the solar and satellite zenith angle. And when you do that correction to all of the bands, it really clears things up. And I'll toggle back and forth again to see the comparison there. The reason we do this is it really will increase the it really makes a high-quality true color image where you get some really vibrant colors, and I'll show in a minute exactly what I mean by that. The next step is to figure out how to simulate the green component. Now remember, we don't have a green on the ABI, but we did have a green component with the Himawari satellite, the Advanced Himawari Imager. So this was a method that was developed by Dr. Steve Miller here at CIRA. Basically what we do is we take lots of different AHI images, and I've just shown one as an example, apply the Rayleigh correction, and that's what the image looks like after the Rayleigh correction. And then find a pixel, for example. You can see the arrow, I'm pointing there in Australia, this brown land area. If we then take the value of the blue component, the red component, and the near IR component, near IR is the 0.86 band, those may be something like 0.17, 0.64, and 0.15, and then we build a three-dimensional lookup table at sort of these as indices. And then we would take the green value at that component, which in this case is 0.32, and then populate this particular grid box with 0.32. That's just one little grid box. Now we do the same thing for lots of different scenes over different times of day, different times of year, and the result is then we have the lookup table built. Now in practice, with GO 16, we would read off the value of the blue, the red, the near IR bands, which is bands 1, 2, and 3, and then find the corresponding green value from the lookup table, and then we have a green component at that point. I realize I've explained this very quickly, and if you want more detail, I can explain more later once we're done. But the bottom line is we can then make very high-quality imagery at full disk, and this is, I should say that we do this on a 1 kilometer grid because the blue band and the near IR band are at 1 kilometer resolution. The red band we degrade down to 1 kilometer, and we actually do have some examples of higher resolution where we sort of build it up to the half kilometer, but the file sizes are quite large, so in order to make the file sizes small, we try to keep it at the 1 kilometer grid. Okay, so now some examples, and this is more of the application side of things. I should also say that we do have a nighttime portion of Geocolor, and the reason we do this is you have the choice when you're looking at this product of either having blackness because it's dark outside since it's a visible product, or we can put something else on there. And it makes a lot more sense to us to actually have some useful product on there at night. And the way it looks is shown here. This is there's multiple layers to this. The bottom layer, which may stand out pretty obviously, is actually a static city lights database that comes from, it's derived from the VIIRS day-night band. It never changes unless we update the database. The reason that it's here is simply for geolocation purposes. Now, in your CWA, I realize most of you know where people live quite well, but this is, I think it's actually kind of useful for the public to see where people live. You can actually sometimes see individual roads that are connecting cities because there's lights along those roads. And it doesn't really get in the way of the meteorological data because it really only shows up clearly when there's no clouds. The other layers are, we have a land mask, and that makes the land a little bit more purple than the ocean. And then the blue, what you're seeing is, what this is the traditional fog product, the 10.3 minus the 3.9, and then that's colored a blue color. And the idea here is to really differentiate the liquid water clouds, which can be fog or stratus. In this particular case over New York and Pennsylvania, you can really see the valleys showing up. This is the valley fog that formed overnight, and this is at about 9Z, a little bit before sunrise. Now, the last layer is actually just the 10.3 band, where the colder colors are colored a grayscale. And you can see some cirrus down here on the lower right, and there's also some cirrus over here on the left. So just adding some annotations, the blue area represents liquid water clouds, so stratus and fog, comes from the 10.3 minus the 3.9. The city lights are just a static background, and then the gray white ice clouds appear as white. And then looping this, you can see as the sun rises, then it transitions into our simulated true color, and we call this altogether Geocolor, where you have the nighttime portion as well as the daytime portion. And it really shows up nice where the fog and the stratus are after the sun rises in the valleys. You get a really nice contrast between the green background areas and clear sky areas and the fog and stratus. Okay, next application. This is one of my favorite applications, actually, and that's smoke detection. So to start off this case, and I should say, it's actually somewhat difficult for us to collect cases on AWIPS, so I can actually do AWIPS screen grabs, and that's due to the fact of how hard it is to archive the AWIPS data. We do have an AWIPS data feed here, an SBN feed at Sierra. However, if we don't capture it within about 6 hours, it's gone. And so most of what I'm going to be showing you is from Macitus, but all of this can be applied to AWIPS, and I'll talk a little bit about that later. So this particular example is just a little, what was this, 17 June, so a little less than a month ago, over southwestern Utah. You probably heard that the fires have gotten really active in the southwestern U.S. over the last month or so. So what we're looking at here is just the 3.9 band 7 by itself, with the color table as a grayscale where the blacker areas, darker areas, represent higher brightness temperatures. And the point here is to show where are the fires located. The first one that you can see pretty obviously is up here over northeastern Utah, but the one of interest is actually here over southwestern Utah. This was the Bryan Head fire, and this was actually the day that it started on 17 June of 2017. And if you look really carefully, you can start to see a bit of a hot spot show up at about 1827 UTC or so. So for fire detection, when first looking for fires, I definitely recommend using the 3.9 band, and that's in addition to some of the level 2 fire detection products that you have and are still being evaluated. There are some RGBs that are useful as well, and those especially are helpful once the fires start to get a little bit hotter. Here's the Geocolor look at that. Now, I'm going to step along slowly so we can actually see when the smoke starts to appear. So we're looking in sort of the southwestern area of Utah, and I'm going to step along and see if we can find when the smoke first starts to appear. And there it is right there, and I don't know if you can see my cursor, but if you can, then you can see that I'm pointing at the smoke. And I'm going to back up and see where the smoke first appears. It's probably right around 1832, but it becomes unambiguous maybe 5 or 10 minutes later. So in this case, the 3.9 band does show the hot spot first, and then 5 to 10 minutes later, you start to see some smoke emerging from that fire. And as we step along, we can let it loop, and you can see now there's actually quite a few fires in the smoke. There's one down here in Arizona. What we're looking at is a little bit pixelated, and that has to do with converting to animated GIF for PowerPoint. It looks better if you don't actually do the conversion. So the smoke really stands out. It actually is a little bit of a different color than some of the surrounding clouds. It's a little bit more of a grayish or bluish color, and that's how the true color aspect of this is actually useful. Rather than just looking at a regular visible band, it's a little bit harder to differentiate between the clouds and the smoke. In this case, some of the cirrus drifting over does look a little bit like that same color as the smoke, but the fact that we have these point sources and coming out is definitely an indicator that this is smoke coming from these fires. Here's another example. This is the same fire a few days later. This was 22 June, and I've just noted where the smoke is, or where the fire is and where the smoke can be seen, and then I'll turn the loop on, and we'll see how well this loops over the webinar. But it's really easy, especially in the morning and in the nights due to the preferential forward scattering, to pick out the location of the smoke. Now, one thing we found from showing some of this to the Weather Service is they really like this for social media purposes because it's really a pretty product. It's really intuitive. You show this to any member of the public, and most everybody would be able to say, yeah, that looks like smoke and not something else. We don't have to have these false colors where the smoke is colored pink or something, where you have to actually have a little bit of training in order to understand what we're seeing. So it's a very intuitive product. And that's in addition to having the actual, I think, useful applications for forecasters themselves, not just for social media. Here's another example. This is the same fire now 2 days later, and this is in the morning, so just as the sun is rising. And this smoke here, you can tell, is actually elevated because it's actually casting a shadow. And if I loop it, you can see then propagating along, and as the sun goes up, the shadow goes away a little bit because we have a higher sun angle. But again, this would be a nice way to tell the public, for example, in northeastern Arizona and northwestern New Mexico, to expect some pretty bad air quality due to smoke from this fire. Now, it's not only good for smoke, it can also see dust. In this case, we're looking out over the Atlantic. Way out on the eastern limb here, you can actually see Africa. This is a tropical depression, or maybe it was a pre-tropical depression. I don't remember, from last week actually, on 6 July. And if I turn the loop on, you can see this large area of brown, and this is Saharan dust which is blowing across. I realize that most of you don't have to worry too much about this. This is mainly an issue for the Hurricane Center, but this is just to show yet another application of how the color of the dust really allows it to easily be picked out with a Geocolor product. And here's an example of blowing dust over Southern California. This was back at the end of March. Oops, let's try that again. This is a little bit more harder to see. You may have to get close to your monitor, but toward the end of the loop, you can definitely see some blowing dust here over the Salton Sea, as well as the leading edge of it. I'm using my cursor to point out right there, and I'll loop it again. And the reason it's a little bit hard to see is because the dust is actually pretty close to the same color as the background, and we really need the animation of this in order to pick it out. So this is something that might be quite useful, of course, in the desert areas or anywhere where you can get blowing dust. That includes the Central Plains and Southern Plains and other areas. Places like West Texas often do get some blowing dust. Okay, so what about AWIPs? So very recently, with help from my colleague Deb Molinar here at NESDA STAR at CIRA, as well as Matt Foster at the Operations Proving Ground, we now are able to get Geocolor in AWIPs too, as well as in AWIPs if you're a national center. And this is the way it looks on the bottom right. These are screen captures from just some random day last week. I think it was Friday whenever I did this. And this is a nice example, again, because you can see in the morning we have the low stratus clouds in blue, and some of the low stratus showing up in the valleys of Missouri and Arkansas. And as we turn it on and let the loop go, you can see the sun rises, and we've got stratus and low clouds, and then the cumulus clouds form just a little bit later. So again, a nice product, useful for identification of the fog and stratus in this particular case, as well as something that might be useful to show to the public via social media. Now, if you look really carefully, you can see the colors everything is not quite as crisp as it was in the other version that I showed you. And the main reason for that is simply due to the fact that in order to get into AWIPs, we have to remap it to Mercator. And when you start remapping imagery, you do lose just a little bit of resolution. But it still looks pretty good, and I think it will provide some use. Now, due to the required calculations, we can't actually produce this on the fly in AWIPs. In other words, we can't take the data that you're getting over SBN and calculate it and make it display like the other RGBs. We have to do the calculations at CIRA and then send them via LDM at sort of the back door in order to get them. But we've gotten the file sizes down to about 12 megabytes each, and you need 3 of those, a red, a green, and a blue. So it's about 36 megabytes or so every 15 minutes. So working with Matt, we decided to start with 15-minute data instead of the 5-minute data in order to conserve bandwidth, and we may increase this later on. And we are sending just the lower 48 states right now. So this is a relatively small domain, and that's how we can keep the file sizes relatively small. Now, I also want to mention that the group up at University of Wisconsin in Sims has come up with a way to display a PseudoTrue Color. This is another RGB. And the advantage here is that you don't have to use a backdoor LDM feed to get it. But the disadvantage is it doesn't look anywhere near as crisp and sort of clear as the Geocolor product. This is an example here that was provided to me just this morning by Scott Lindstrom. Also, it's only currently available at the 6-kilometer full disk resolution, and it's 15-minute data, but in the future they do hope to provide the full resolution data. Again, no Rayleigh correction means that the colors are muted, and it looks not quite as crisp. And they do expect to include this as part of an upcoming RPM. When you download it, you should be able to find this particular product on your AWIPs. But if you want the setup instructions now before the RPM comes out, you can email Scott Lindstrom. So takeaways here, if you're interested in pulling in and evaluating this product in your AWIPs, shoot me an email after the webinar, and I will pass along Matt Foster's setup instructions. We've had a few guinea pigs. I think Boulder is now pulling this in, as well as Medford, Oregon, and maybe a couple of others, but we hope to get more offices to start taking a look at it. Our initial goal is to get feedback. We want to know whether you think this is useful from an operational perspective. Additionally, the Operations Proving Ground, specifically Chad Gravel, plan to run an evaluation of this pretty soon. So also let him know if you're interested in participating in this evaluation. This will probably happen in a few weeks, so go ahead and let him know now, and then he can add you to the list of when the evaluation actually begins. Now, in the longer term, we do hope that this product will eventually be produced at NESDIS and provided via the NOAA port SBN, and that way you won't have to worry about getting it through the back door. However, as you probably know, getting anything into operations takes a pretty good bit of time, so this will take a while. And additionally, and perhaps most importantly, in order to make this happen, we really need a formal request by the NWS. They have to basically say that this is a requirement, this is something we really need. So if you like this product, if you think it's useful in any way, I encourage you to pass that information up the chain to your SUE, to your MIC, and then pass it along to the region, and then hopefully we can get a formal request for this to become operational someday. And that'll just make things easier for everybody. And I think that's all. I'll take any questions now.
Hi, Dan. This is Scott. I'll just mention that in that Sims produced RGB, you might have noticed a white background, and that's there because it's using the 0.64, and which of course becomes black and speckly as you get a higher and higher sun angle. So when that problem is fixed, you can get rid of that white crescent by making the background black because you won't have these missing values in the 0.64.
Great.
I hope that made sense.
Yeah, it did, and I think they're supposed to fix that black pixel issue any day now, sometime this month.
Any questions for Dan or comments? Okay, well, we want to thank Dan for leading this presentation, and the next webinar will be on July 26th, and Chris White will be leading it, and he'll be talking about the nighttime microphysics RGB. Thanks, everybody, and have a great day.